All right. Hello, everyone. Welcome to join the third Innovations in Digital Design webinar. The webinar features two exceptional speakers. One is Dr. Xin Yan, and one is Albert Li. So they will discuss the research and application in structural topology optimization, incorporating subjective preference. The first one will welcome Dr. Xin Yan to discuss design details control strategies for structural topology optimization. Dr. Xin Yan is an architect with a comprehensive background in mechanics and computer science. Currently, he's a postdoc researcher at Future Lab and Tsinghua University. He received his Ph.D. in architecture and urban design and Master of Architectural and Civil Engineering from the University of Chinese Academy of Science in 2022 and 2016, respectively. He's graduated from Theoretical and Applied Mechanics at the University of Science and Technology of China in 2013. In 2019, he also carried out his research work at Structural Topology Optimization at the Center for Innovative Structure and Material at RMIT University, Australia. Let's welcome Dr. Xin Yan to share the screen.
Okay, thank you for the introduction. And let me share my screen. So can you hear me and see the screen?
Okay.
Okay. So it is an honor for me to show some of my works about the topology optimization design. And good morning, afternoon, and evening, everyone. I'm Xin Yan from Future Lab at Tsinghua University, and today my topic is about the design detailed control strategies for structural topology optimization. So, this is just the description of my work and study histories. So, the background of this research is that in the past 20 years, there are so many famous architectures or structural components generated by the topology optimization algorithms. As you can see, there are 7 very famous examples of the design. So each one of them has a very organic and elegant form with the very high structural performance. So what is the topology optimization? The topology optimization method is just with a very clear and simple logic. So as you can see, the left one is the working flow of the BISO method, which means bidirectional evolutionary structural optimization, which is developed by Professor Yiming Maxie, which is the supervisor of me and Dr. Li Zhi. So he just developed this method to optimize the structure under some specific loading case. As you can see, there is one example about the 2D cantilever. Firstly, we can just make a 2D plan design domain, and we fix the left boundary like the right lines. And then we just add the load case, a point load in the center of the right side. So with the help of finity element analysis, which is FEA for short, we can calculate the mechanical values in all the elements. So each element have its own mechanical values, and then the algorithm can just compare the mechanical values, and we can choose the element with the very low mechanical values to be removed from the whole design domain. With this method, we can just reduce the materials in each step. And when we just go in this loop, we can optimize the whole structure. So you can see there are 6 classical streets for the whole design, and then finally we can generate a very you can say it's a very special and logic structures which can also have a very high structural performance. So, but the conventional topology optimization has their own problems. They have limited application conditions in the early stage of the architecture concept design, because when as a designers, when we design our own work, we need to compare our own design objects with the structural preference. So this is a very important thing for us, because if we just depends on the computer and just use the computer, what the computer tell us which one is good and which one is bad, is not work of us. So, but when we use the conventional topology optimization, we usually do something like this one. Firstly, we make an initial model like the green one, and we just maybe we can image what's the outcomes, what's the final results. We want to the final result like this one. There are some standard structural components with very small holes overall design domain. And then we just start the optimization algorithms, and we have nothing to do but wait, and wait. And finally, the algorithm finish is optimization, and we just want to get a very good design, but the outcome is like this one. We can see the final result the computers give us is a very it's hard to say, is with the highest structural performance, but is not what we want. So the question is, can we pre-design the details before optimization, and how to control the design features with topology optimization? So this is the intentions of my work. And to finish, to achieve these goals, firstly, I just construct a framework, BISO framework oriented to the architecture design. So in the conventional BISO logic, we just write Python code and random in the Python environment. We have nothing to choose, and then in my work we just divided the whole logic into several parts. Firstly, we can make a model in the Rhino or SketchUp or 3D Max or just any other 3D softwares, and we can use the Grasshopper or some scripts to transform the 3D model into some TXT files, so which contains all the geometric information about the model, and we can transfer the TXT information into the FEA platform, just like Abacus, and then use the Python code to control all the loop and generate the TXT files contain, which includes the results information, and then we just transfer the TXT files to the Rhino environment back and get the final 3D results. With this framework, we can easily generate a very beautiful initial design domain with a freedom surface or with very complex forms. And then we can just use the Grasshopper to generate its calculation network. And we can get all the information about the FEA elements we need and then transfer the information into the TSC files and transfer the numbers, the values into the BSO loop. So with this framework, we just design and fabricate some installation like XForm 1 with Dr. Nick Bao and Professor Max Xie, and XForm 2 in the 2019 at Barcelona exhibition, also with the Dr. Nick Bao and Professor Max Xie. And we also do some computation, which means structural computation to generate the most highest structural performance result. So this is the basic logic of the framework, but this is also not fit our goal about the pre-designed form details. So I just changed the framework with the right part, which is artificial coefficients files. This one is just contains some parameters. And with this kind of parameters, we can change the basic BSO logic and to add our design goals, our design preference to the structural optimization. So there are 6 new algorithms I developed in the past 2 years. And the first one is the original BSO logic. So you can see the right part is the artificial coefficient files I made. And we in this algorithm, I just add some parameters into the topological optimization algorithm, and then just integrate our design concepts with the structural calculation and mix them together to get another design, which is at some level can fit our design goals. So the first one is geometric constant. You can see this is an example about the high-rise building. We just fix the bottom boundary and add the wind load at the 2 sides of this building. And with the original BSO method, we can just optimize the structure like this one. So you can see in the final result, there are some asymmetrical parts here and here. So why we get asymmetrical parts? The reason is one is because the calculation errors in the computer, and then the most important one is when we reduce the materials, which means when we remove the elements, or maybe the elements in the symmetrical positions are not reduced at the same time. So when one element is reduced and the other one is still here, and then from that point, the following results goes to the asymmetrical. So I just made a SYM BSO, which is symmetrical modified BSO method. In this method, I just coupling the symmetrical elements and add their mechanical values together to generate a new value, which means sensitivity number. And then based on the new sensitivity number, I can just remove the symmetrical elements together. So in each part, in each step, we can get a symmetrical symmetrical results. So you can see with this algorithm, we can always generate the symmetrical result. And the second one is with the similar logic. When we optimize the periodic structure with the conventional Bissell method, it's hard for us to generate a very regular outcomes because there are so many elements in the periodic parts. So we need to calculation all the elements values together and then remove them or preserve them at the same time. So with the CYC Bissell method, we can generate our results with the periodic features. So you can compare the outcomes. This one is generated by the original Bissell. So you can see there are some periodic parts here. And then with the CYC Bissell, we can just add the periodic constraint to the algorithm and generate a form with the periodic features. And the third one is just a little method because this is still with some calculation errors in the FEA process. When we generate a design under the gravity, the Bissell method may face a problem like this one. So when we in the middle of the evolutionary process, we can just generate some small parts, which has no supports around it. So in the next calculation, this small part will just fall down without any support. So if this thing happens, all the FEA calculation will stop because there is a very big displacement. So to deal with to solve this problem, we just need to remove the isolate part before the calculation start. But the question is how we can find the small parts without any supports in the optimization algorithm. So we just use the depth first search method to search for the isolate part. And then with the DFS method, we can just divide we can just select which one is the small part without any supports and remove them firstly, and then transfer the remaining structure to the next calculation. And the second strategy is the pre-design with multi-radius. Yeah, the multi-radius Bissell is just a change a very important parameter named RMIN in Bissell method. In RMIN Bissell in the conventional Bissell method, RMIN is just a very important parameter to control the local size in the final result. This value is like it's like the size to smooth the local mechanical values. So with the RMN value, we can generate a part. We can generate the final part with the similar size. So in the original Bissell method, we can only set the one RMI value for each element. And then we just generate a part with the similar size around the whole design domain. But if we can encrypt the different element with different RMI value, we can pre-design the local size in the final result, like the diagram here. So, which means if this part is if this element is encrypted with a bigger RMI value, and the right one is with the small RMI value, then with the MR BSO method we can generate a final structure with the very huge blue parts and very small red parts. So with this kind of method, we can just use the RMI value to pre-design the final features in the optimized result. So just back to the 2D cantilever algorithm. So if we add the different RMI value from 10.5 in the of the left part to the 1.5 millimeters in the right part, we can generate a final result like this one. You can see with the very big RMI value on the left, we can generate the very huge structural components here. And with the small RMI value on the right, we can generate some slender parts. This is generated by the original BSO method. So you can see the difference. Also, the building, the high-rise building example can be generated like this one. With the MR BSO method, we can just set the bottom RMIN value about 3 meters. Oh, sorry, 15 meters. And the top one is with 3 meters. So you can see the structural features from the bottom to the top is from the huge to the small. So this is the shell dome examples. The deep parts, deep right parts means the elements with a bigger RMI value, and the light pink part means represents the elements with the smaller RMI value. So we can just pre-design the relevant geometric features before the optimization starts. So similar, we can get this one. You can see the fifth one. Red part means the element is encrypted with a bigger value, and we can generate a very huge components here. And the blue part means the elements are pre-designed with the smaller RMI value, so we can just very small components near it. And the third strategy is pre-design with multi-volume. So in the original BSO method, we have only one volume fraction, which means maybe if you set the volume fraction as 15%, it means you will remove 50% elements away and hold half materials in the final result. But if you just have the only one volume fraction around the whole design domain, sometimes it will happen like this one. So when the original BSO method optimized the whole design domain, there are some parts totally void and some parts with totally solid, because the right, maybe the left part is more important for the structural performance, and the right part is not that important. But for the function, for the architectural function, maybe sometimes we need some materials near the right part, and we also need to dig some holes near the left parts, like the blue one and red one. So MVP, so we can with MVP, so we can just add more local volume fractions into the different parts, and the algorithm can optimize at the same time, but reduce different materials in the local parts. So this is a 2D cantilever example. When we just develop the whole design domain in two parts, and we can maybe we can just change the different local elements. Maybe from the case file means the each parts have the same volume fraction, and case one and case 9 have the totally different volume fraction. So you can see when we add the volume fraction of part 2 bigger, we can in the case 9 we just have a very huge structure in the right, and very slender components in the left. So with the different in the subdomain diagram and with different local volume fractions, we can generate a totally different design, and we can control the local materials in the final result. So this method maybe is very important for the high-rise building design, because in the original Bissell method, we can only have the whole one design domain, and we generate a structure have more materials at the bottom, and there are very small components on the top. So if we just divide the whole design domain into several parts, like 6 sub-design domains, or 12 sub-design domains, or 18, we can generate different designs. So with the sub-design domains, we can just calculate their own volume fraction at the same time. So we can dig some holes in the this one is a very good example for compare the original Bissell with the MV Bissell. With the original Bissell, we can generate final result like this one. But for the building design, the bottom part is very expensive for the we must dig some holes as the doors or windows to let the people or light come in. But for the structural performance, if you dig some holes at the bottom, will have a very big effect on the structural performance. So if we just divide the whole design domain into 12 levels, we can make some bigger holes and add some more windows in the bottom parts. Also have some more materials, structural materials on the top. That's what we want, because when we design a building, we can it's not only depends on the structural performance. We also need to compare other structural requirements. Not structural requirements. We need to think about the aesthetic or the function requirements. So this is an example about the shell design domain. The shell design with different sub-design domains, we can generate different parts. So you can see if you have a very in the original Bisel method, we can generate a structure like this one. So the center part have no holes inside it, because the central part is very important for structural performance. But if we just design a shell roof of a building, maybe we need to dig some holes near the central part. So you can just add more sub-design domains in the initial design, and then with the different volume fractions, we can just dig some holes near the central part logically. So also we can generate some very special shell design domain with the MV-Bisel method, because we can draw some different patterns on the top, and then set the different local volume fractions of the different parts. So we can pre-design the whole the geometric features of the whole design. So you can, if you want to make some big holes at this part, you will just set a very low volume fraction of in this part. And then if you just maybe you want to some bigger structures here, so you can just add the local volumes fractions to the a higher level. So this example is about the Olympic National Stadium. When we use the Bisel method to generate it, the first one is the example we are familiar with. This is the original design of the bird nest, and the level 2 is the design with the original Bisel method. So you can see this design is the best one from the perspective of structure, but it's not a good design from the perspective of architecture, because there are so many materials at the two corners, and very big holes in the middle part, which is not look like don't look like a bird nest. So if we use the MV-Bisel method, we can just divide the whole design domain into many parts. So like 25 subdomains, 100 and 400. So with MV-Bisel method, we can generate a final result with more slender structural components and with more small holes overall all the structure. And the last one is pre-design with multi-weight. In the Bisel method, the very important value is the elemental mechanic value after FEA calculation. So this value is the parameter for us to choose which one element should be removed and which one should be contained. But this value in the original Bisel just care about the loading, the structural performance. And if we want to add maybe some drawing or some diagram into the algorithm, we can add another value into the calculation of the sensitivity number, like this one. So this one is about the loading, the structural loading, And this one is about the graphic parts. You just a human add some drawing to it. So this the MW Visual can just compare these two information and mix them together to generate some different designs. This 2D cantilever can just if we add a drawing like this one, which means in the left part we add arrows like this one, and we maybe the designer just need to add a structure near the left part, but components like this has very limited contribution to the structural performance. So if you add this pattern, you can generate parts in the final result with MW Visual. And if you just reduce the weight of the graphic, you can just return to the original Visual result. So MW Visual equip you with choose. You can just reduce the materials at any time, at any level. So if you have a very big goals to have a very, I must have components here, you can just add the weight of graphic to a bigger value. And if you just want to have a try, if the components is really unimportant for structural performance, you can accept it can be removed. You will just need a weight of graphic to a very small value. So with this kind of method, you can add some geometric features inside the final result. Also, if you don't want to add graphic patterns, you can also add the different ways about different loading cases. So for the dome design, this one, the bottom left one, is generated only with the gravity loading. And this one, the first one, is only with the torsion in the center. So you can see the totally different patterns. For the first one, which means the torsion in the centers, it will generate some curved parts like the red lines. And if you just calculation and gravity, you will generate some straight components from the boundary to the center. So if you change the weight of gravity or torsion, so you can just adjust the curve, the structure local components from curved lines to the straight lines. So this is a real project designed by the MW Visual in 2020 at Shanghai in Tongji campus. So when we designed this installation, we just made a initial design domain like this. So it's a wall, it's a concrete wall. And we just add a first load is shear force on the top, and add two windfalls to at the two different surface, and fix the three points. So when we use the original Visual, we just generate the final design like this one. This one is not what we want, because the top parts have no holes, but the middle parts have so many big holes. So we just use the 2D example to generate a 2D optimized pattern, and then transfer the pattern to the MWBSO and generate the the weight parameters, which is which is the artificial coefficient fields to the MWBSO, and then we can just compare the three information and mix them together, which means we set the weight of the loading case to the 99% and the artificial intervention pattern with the weight of only 1%, but the final result is totally different from the original BSO design. So you can see with this settings and with MWBSO, we can just add we can just generate a design like this one. It's totally different from the original BSO, right? It's totally different from this one. So if you compare the MWBSO optimized result with the with the patterns we transfer to, you can see the MWBSO add a structure components in the middle to support the whole structure and add the whole structure, encrypt the whole structure with a higher structural performance. So this is the final installation in Tongji Compass. So that's the work of mine in the 2 years, and that's all of my today's presentation. Thank you.
Thank you, Dr. Xinyan. And we're going to ask some questions about Dr. Xinyan. If you have any questions, please feel free to unmute yourself, or you can type for the comments. And if there is any questions on YouTube live, when you're if you're still looking at it, you can type in the comments, and when we see, we will tell Dr. Xinyan. Thanks.
Hello, can you hear me?
Hello. Yeah.
Hello. Hello, Dr. Yan. Thank you for your amazing presentation. And I have a question for the MWBSO for in your bird nest example.
Yeah.
How's the performance loss when you use different resolution resolution of subdomain? Performance loss.
In this presentation, I didn't add the information about the value, the structure loads. So if you, but the information is, so let me open my paper.
Okay.
It's to give the information about the component, the structure loads. Yeah. So, sorry.
This one. Just okay.
This one. So this is the initial design, which is the real project, and this is the BSO parts, BSO result, and this is the 3 design with 25 sub-design domain, 100 and 500. So with the different loading cases, we generate, we just compare all the results with the BSO method. So you can see at the earthquake force, maybe the BSO method is the good one. Yeah, the best one.
Yeah, I
But
understand.
for the torsion in the center, you can see the MV so is the best one. And initial design is also good. But for the gravity MV so is also good for compared to these two. So I think it depends on what you want to optimize, because in this example I just add all the loader case in together to reduce the materials. So I think the MV so can generate the structure with small holes, so which is much better for the torsion in the center.
Okay,
But
understand.
yeah.
Yeah. Thank you for your answer. And I have another question, that is, when you developed this algorithm, I remember you used Python. But when I use Python, I noticed that only float numbers are allowed, not double. But when we use Bezier method, we have a design variable. We need a very small design exponent. Is that? I remember that. Yeah. But how you use Python to support this very small number, because it may execute the limitation of float number.
Actually, I haven't encountered with the problem about the float limitation.
Okay.
So
We
yeah.
can discuss later.
Yeah. But I can see maybe you can try to identify the float number and then just calculate back to the result. So I mean, in the middle process, you can just amplify the float number if the float number is too small, and you generate it, you calculate it, and then go back to the real value. I mean, divided the value. Yeah.
Okay, I think this is a question about numerical accuracy, but now it's
Yeah.
okay. I understand. We can discuss later. That's fine.
Yeah,
Thank you
yeah.
for your thoughts.
Thank you.
That's all my questions. Thank you.
Thank you.
If we don't have more questions, we can switch to the second speaker, which is
Okay.
Albert Lee.
Thank you.
Thank you.
And let me introduce Albert first. Albert is a PhD candidate at the Center for Innovative Structures and Materials at RMIT University. After completing his Bachelor of Arts degree at Tianjin University in 2018, he embarked on the PhD program in civil engineering in 2020. Albert's active research area includes structural optimization, computational design, discrete geometry processing, and digital fabrication. Let's welcome Albert for his topic, interactive structural topology optimization with subjective scrolling and drawing systems.
Okay, thank you for everyone. Welcome to join this presentation. I'm Albert Lee. I'm glad to share my recent research in interactive structural topology optimization with subjective scoring and drawing systems, which was supervised by distinguished Professor Mike Xie, Dr. Jeff Lee, and Professor Roland Snopes. The outline of this presentation includes 6 parts. Firstly, I'm going to introduce the background of this research. Secondly, the proposed SPBSO method will be illustrated. Thirdly, I will show the released digital design tool, IBSO, which is developed based on the SPBSO method, followed by parametric investigations and the practical applications will be introduced, and a conclusion to summarize all findings. Topology optimization is a generative design technique that can create lightweight and high-performance structures by distributing materials in design domain. Conventional topology optimization methods rely on finite element analysis. This technique can calculate the local structure performance of discrete elements, as shown on the screen. Based on the quantified values, topology optimization can iteratively explore the most efficient structure form according to the input design domain, loading and boundary conditions, and volume constraint. Among many topology optimization methods, a widely used technique is the bidirectional structure optimization method, so-called the BISO method, which is proposed by Professor Mike Xie and Professor Xiaodong Huang. This technique can add and remove finite elements simultaneously to improve material distribution. In recent years, this technique has been used in various structural designs, including bridges, furniture, and architectural design, as shown on the screen. However, existing topology optimization techniques are purely based on structure performance, which means that the results cannot always satisfy all design requirements, such as personalities, fabrication costs, and aesthetics. To overcome this bottleneck, recent research has developed multi-solution strategies based on the BISO method. Such approaches sacrifice a small amount of structural performance in exchange for diverse design options. The obtained solutions have different shapes while maintaining a high level of structural efficiency. The existing strategies can be achieved by introducing randomness to disturb the optimization process, changing the optimization settings, and adding structural complexity control. However, although multi-solution strategies can provide many design options, finding the desired design is a difficult task. One reason is that evaluating each design option is time-consuming. Another reason is that real solutions can satisfy design requirements according to differences in personality. Therefore, too many design options can lead to a high cost in selecting a satisfying design. This is called the overchoice problem. So, what is a good design process? The design exploration is an evolutionary process rather than choosing an appropriate outcome from various options. Designers should add their subjective considerations to guide the design process. As a result, the optimization process should allow more subjective involvement. It should be noticed that different design tasks require different levels of subjective involvement, where low and high levels of involvement can result in performance-driven and preferences-driven design, respectively. Performance-driven design don't need too much subjective involvement. Hence, they are suitable for applications where structural performance is important, such as bridge design and mechanic design. Although such designs can create high-performance configurations, designers typically fail to add their creative ideas to affect the final outcomes, meaning designers have to passively accept the optimal solution. On the other hand, preferences-driven design focus on creativity and aesthetics, and they are less concerned about objective performance. Thus, the key geometric feature of the final design can be fully controlled by subjective preferences like furniture design and jewelry design. So the optimization process is utilized as a supporting role in design exploration. However, few studies have focused on topology optimization based on subjective preferences, which is an ongoing challenge and remains underexplored. To solve the above issue, our research proposed a new topology optimization method considering subjective preferences, named SP-BISO. It is based on the BISO method. Let's look at how this method works. The stiffness maximization problem subjected to a volume constraint can be formulated as shown on the screen. Among many steps in the BISO framework, an important part is sensitivity analysis, which can rank the elements according to the results of finite element analysis. The ranked elements can be optimized using the bisection method to create the optimal design. In other words, the sensitivity field represents the consideration of structural performance and decides the formation of a final design. So, if we visualize the elemental sensitivity field with a texture, we can obtain a grayscale image, which will be useful in the following steps. To generate multiple solutions, this study introduced the random perturbation method proposed by Yunzhen He. In their method, the sensitivity number alpha is penalized by a random coefficient beta, which affects the selection of elements being added or removed. Moreover, the generation of random coefficients is driven by the random seed integer gamma, where different gamma can result in different sets of random coefficients. Due to this, infinite solutions can be obtained by modifying gamma, thereby significantly improving the design diversity of topology optimization. If we also visualize the random perturbation field with a texture, the multi-solution method can be understood to multiply these two fields during sensitivity analysis. Next, let's introduce subjective preferences. This study proposed a simple approach to quantify subjective preferences by scoring the existing solutions. The subjective scores are used as weights in topology optimization to generate new designs. To clearly introduce the proposed method, we call the existing design to parent design, and the subsequent new designs are child designs. The scoring weight, omega s, is used to penalize the elemental sensitivity number. The modified sensitivity number alpha s can be calculated by the equation shown on the screen. S is the subjective score. When S is smaller than 0, the parent design is considered an undesired solution. When S is larger than 0, the parent design becomes a preferred solution. Lambda s is a scoring parameter ranging from 0 to 1, which allows users to control the influence of scoring weights on topology optimization. Another strategy to consider subjective preferences is using hand-drawn patterns. Drawings allow designers to show their creative ideas. However, it is difficult for designers who lack structural design experience to produce high-performance sketches. Due to this, we convert the given drawing pattern into drawing weights to modify the elemental sensitivity number. In doing so, these numbers can guide the optimization process to achieve a satisfying designs. In detail, a drawing pattern is first translated to a grayscale texture made up of pixels. The colors of pixels are used to calculate the drawing weight omega d. Then, the modified sensitivity number alpha d can be calculated by the equations shown on the screen. Note that controlling the two parameters lambda e and lambda d allow users to balance objective structural performance with subjective preferences according to design requirements. Finally, a new design integrated with the drawing pattern is created. Also, the drawing system can be based on the existing solution. First, the nodal sensitivity field of the existing design can be converted to a texture. Using the bilinear interpolation method. Next, users can draw or remove some structural members from the texture. The texture is then used to calculate the drawing width for the subsequent topology optimization. Finally, a new design is created based on the updated drawing width. Now, let's sum up all techniques together. The SPBSO method is proposed based on the combination of the multi-solution strategy, subjective scoring, and drawing systems. The integrated sensitivity number used in the SPBSO is shown on the screen. From the field perspective, the updated sensitivity field equals the random perturbation field times the scoring field times the addition of the raw sensitivity field and the drawing field. The computational workflow of the proposed method is summarized in the flowchart shown on the right. The new features are highlighted. As can be seen that by alternately inputting subjective preferences and executing topology optimization, users can iteratively explore the desired design. In this way, a human-centered design exploration is created. To further explore the capability of the proposed SPBSO method, a user-friendly digital design tool, IBSO, is developed. It has three unique systems: the multi-solution system, the scoring system, and the drawing system. The implementation of IBSO is achieved by using both C++ and C# programming languages. The C++ part contributes an efficient optimization kernel, which is modified based on existing optimization code. The C# part gives the graphical user interface, allowing users to change parameters and define boundary conditions interactively. The IBSO software can run 4 SPBSO solvers simultaneously. This allows 4 parent designs to be parallel evaluated and further modified based on subjective preferences, resulting in child designs through subsequent topology optimization. The evaluation and modification process can be repeated until an ideal structural design is obtained. Next, I will show the features of IBSO through a video.
Game over. Game over. Game over. Game over.
Okay, thank you for watching. In this study, we conducted two sets of parametric investigations using the IBISO software. To compare two given structural topologies, three metrics are used to quantify the differences in shape and structure performance. Firstly, the difference in structure performance can be represented by the compliance ratio, delta C. Secondly, the overlapping rate P can be used to measure the similarity of the two solutions. The calculation of the overlapping rate is shown on the screen. For example, the blue design is solution A and the green design is solution B. Their overlapping part is the yellow area shown on the screen. We can find the overlapping rate is 89%. Note that the overlapping rate alone is inefficient to show the geometric difference. Hence, the third metric, delta G, is used to measure the difference in the number of holes. Mathematically, the number of holes in a solution can be calculated based on the geometric information of the obtained mesh model. For example, solution A has 3 holes, solution B has 5 holes. The delta G equals GB minus JA equals 2. In the following study, solution A and solution B are considered highly similar, then delta C approximates 1, P approximates 1, and delta G approximates 0. Let's look at a classic 2D short cantilever example. The optimization settings are shown on the screen. In the parametric investigations, we regard the original BISO result as the parent design. Then we test the influence of scoring weights on optimization results by changing the subjective score S and the scoring parameter lambda S. All the tests are based on the same parent design with lambda S equals to 0.1, 0.5, and 1, and S equals to -3, -1, 1, and 3. Therefore, 12 child designs are created. They are then compared with their parent design using the proposed metrics. To avoid interference with the drawing system, lambda D and lambda E are set to 0 and 1 respectively. The results of testing the scoring weights are shown on the screen. Firstly, it can be seen that the solution A and B with deselect scores have different shapes. All the overlapping rate P are less than 90%, and the lowest case has almost 50%. When lambda S increases, P becomes smaller. Besides, Most delta G are not zero, meaning the child designs are different from their parents. Together, this result indicates that the disliked score can result in diverse solutions. In contrast, solutions C and D have preferred scores, so their shapes are similar to the parent design. As shown on the screen, as can be seen that their P are relatively high, ranging from 89% to 98%, and the delta G is either 0 or -2. Moreover, either high or low lambda s can make the child design close to the parent design because they have already been the preferred solutions. It indicated that the preferred score can result in similar designs to the parent design. In terms of structural performance, there is just a little difference between these 12 solutions. The maximum performance loss is 3.8%. Other designs have performance variations within 2%. The evaluation history figures are shown on the right. Together, it can be concluded that both lambda s and s can control the formation of final topologies. In the following investigations, we test the influence of drawing widths using 5 child designs. The drawing pattern is a creative sketch as shown on the screen. The 5 child designs are created using different combinations of lambda d and lambda e, which can be further represented by delta lambda. The parameter settings are listed on the screen. Then the child designs are compared with 2 reference designs. Reference 1 is the original Bissell result. Reference 2 is the drawing pattern redesigned using topology optimization to achieve the target volume. The 5 child designs obtained using different combinations are shown on the screen. If we set a low delta lambda, the child design will tend to be similar to reference 1. But if we set a high delta lambda, the child designs tend to be similar to reference 2. This indicated that delta lambda plays an important role in determining whether the child designs are performance-driven or preferences-driven. This statement is supported by their compliance values and similarities. The bottom left graph shows the evolutionary history of child designs. The bottom right figure shows the overlapping rate of the child designs compared with the 2 references. It can be concluded that although performance loss may be unavoided using drawing widths, the child design has the potential to meet multiple design requirements and inspire designers. In addition, we use 2 examples to demonstrate the potential of the proposed method in practical applications. The first example is a simple 2D bridge. As shown on the screen, the size of a bridge is designed to be 240 mm wide and 80 mm tall. Due to symmetry, only half of the structure needs to be modeled. The loading and boundary conditions of the bridge are shown on the screen. The design target is to achieve many holes in the structure topology as possible. It is also desirable to obtain a final design that is performance-driven but includes subjective considerations. After running a Bissell, the first 4 parent designs are obtained by purely performance-driven settings. As can be seen that solution A and B have more holes. Hence, they are considered preferred candidates to create the next generation. The 4 new solutions are created using the scoring system. The scores are 4, 4, -4, and 4, -1 respectively. Interestingly, all child designs have 11 holes, and their performance loss is within 4%. Comparing these solutions, their hole arrangements are different, where A to C are arranged as 3, 5, 3, but solution D has 8 8 holes at the bottom of the bridge. Thus, we pick it as the preferred design and use the drawing system to improve it further. Then, a manually drawn pattern is used to create a new generation of child designs. All solutions have a highly similar shape with 13 holes and structural performance. Here, solution A is selected as the final design because it has the best performance. The second example is a 2D chair, which is a preferences-driven task. The design domain is designed to be 80 millimeter deep and 80 millimeter tall. The seat and the backrest part are set as a continuous passively solid domain, subjected to a uniform load of 1 Newton per millimeter. 2 points are fixed at the bottom of the design domain. The design target is set to maintain subjective ideas while improving structural performance. Reference 1 shown on the screen is a purely Bissell result, and reference 2 is a curved chair design inspired by Frank Gehry's. It is created by using purely preferences-driven design settings. The figure shown below is the first generation is obtained by lambda E equals 1 and lambda D equals 0.5, aiming to achieve improved structural performance with a small distortion of the drawing pattern. As can be seen that all child designs have successfully preserved the drawing pattern with additional members, which enhance the structural performance. Next, decreasing lambda D and can further improve design diversity, as shown in the figure below, where the key geometric features are partly kept and their performance has a significant improvement. This example clearly demonstrates that the structural performance is not the only consideration in structural design. Creative ideas to improve aesthetic quality and achieve other design requirements are also valuable considerations. In conclusion, the contributions of this study include: we proposed an interactive topology optimization method considering subjective preferences. The proposed method includes subjective scoring and drawing systems. Using the proposed method, diverse innovative designs can be created while maintaining a high level of structural efficiency. A digital design tool is developed to assist design exploration using multiple optimizers. Design parameters can control final topologies to be performance-driven or preferences-driven. The full paper has been published on computer IDD design. This is a reference list. Finally, I would like to thank distinguished Professor Mike Xie, Dr. Jeff Lee, and Professor Roland Snokes for their supervision. Thanks to Mary for helping me prepare the presentation. Thanks to Dr. Xin Yan, Professor Weixin Huang, and everyone in CSM for the advice and support. Thank you for your attention.
Thank you, Albert. It was an amazing lecture and very inspiring. I especially like the IBISO software part because it reminds me somehow about Midjourney and generate like 4 different images for different kind of methods, but with the same or with the similar structural performance. And I have like 2 questions about the IBISO software. One is that because you're actually drawing the solution, you make a drawing first or upload the image, and then you generate the results. So I would like to ask, first thing is that, can you upscale the results? For example, right now you currently have the radius or like the scale to change it, and can you upscale it to a bigger image or bigger plan? And second question is that right now I see all the thing is like the analytical result is done in 2D. Is there a way or is there a potential to make it from 2D results go into 3D 3D structural analytic results. Thanks.
Okay. Okay. Thank you for your question. Amazing question. The first, I will answer the first question. Firstly, I haven't implemented the upscale function in IB, so this is because I just I think it is not a very complex function. So this is the publication stage. I just published a paper and software. I haven't considered too much about user interaction and some commercial applications. But from the principle, that is very easy because you can just apply to change the texture with different resolution or something. You can apply using the different texture. You can create different solutions, I guess. And for the second question, for the 3D, there are a lot of challenges. For example, you can't drawing on space. Yeah, this is a great challenge. So this is why drawing system haven't been considered to extending to 3D cases, but scoring it is possible. I think in my future research, I will develop the 3D version because our reality is 3D, our world is 3D. We need to design 3D structures. I think maybe next year you will see the result. Thanks. Thank you for your question.
Looking forward to it. Thank you for your answer. Any more questions? So if not, if you have more questions, please feel free to email either Bilibili or Dr. Xinyan for like more suggestions, advice, comments, and questions. Thank you. And please let me introduce IDD in the end. IDD, which we called Innovations in Digital Design, is an online platform for sharing innovative research, ideas, and design works in the digital design field. We aim to explore the nature and future of design by showcasing the outstanding work of young generations, designers, and scholars from all over the world. IDD operates once per month, offering oral presentations, discussions, and online courses in English. All recordings are uploaded to YouTube, and we're now trying to upload it to Bilibili as well. And all the recordings are available for free to all. And please feel free to submit your application, your proposal, your abstracts to us on your website, the Innovations in Digital Design website. And feel free to join us if you liked it. And thank you all for today coming to our webinar. And we're done for now. Thank you. Bye.